Carlos. I give like a very overall view of the project I've been working on for this time. It's essentially a proof of concept of distributed acoustic sensing instrumentation suitable for tsunami wave detection. This project is carried out in a collaboration between Geoazur and Universidad de Alcalá in Spain. And let's move on. Huh? Let's share your screen. Do I say got it? No, got it. That's good. I think it's okay. We cannot see them. See you. Okay. All right. So this is just a general roadmap of where I'm taking you guys. So I'll just give a general context, motivation for the study, give a brief description of the DAS instrumentation we're using, what type of signals we're planning to detect due to the tsunami itself. And finally, I'll just give an overall description of data set that we've been validating our model with. So I guess not to start with an alarmist tone to the talk here, but what I'm showing here is the Global Risk Index, which not only evaluates the risk and potential impact for a natural disaster for a country, but it also takes into account the overall social situation or the context of the country. This means essentially their ability to cope, their ability to adapt to such disasters. And we can already see that there's a somewhat of a heterogeneous distribution for the Global Risk Index. Some of this is due to geographical location, but it also is a factor of the social context. For the most part, this is due to poverty or inequality, lack of access. And in the bottom over here, I'm showing the number of the number of casualties or deaths for different types of natural disasters over about the last century or so. The size of the bubbles corresponds to the number of fatalities. We can already see that at least for this last century, most of the fatalities are due to droughts, floods, and to some extent earthquakes as well. We can see also that for the last few decades, we actually done a pretty good job at reducing the number of deaths, except for earthquakes and well, perhaps storms or very difficult storms. On the earthquake axis, it's worth mentioning that some of these events are also include deaths due to tsunamis. So you have the Tohoku earthquake, you have the Sumatra earthquake, and you also have two tsunamis that occurred in Japan and in China in the 1920s. I'm stuck. Yes. Oh, changed. Okay. And well, the best way to mitigate the impact of such events is with having the ability to predict them. And in our efforts to predict such catastrophes, there's been a plethora of monitoring and forecasting systems that have been deployed or designed throughout the time. And all of these have the primary intention of generating and launching an alarm in order to give the possibly impacted community sufficient time to take necessary precautions to evacuate and the such. So what I'm showing here are the multiple types of natural disasters along with their spatial extent or their footprint, along with their average duration for each of them. So in general, for example, for droughts, we can roughly estimate them about a month in advance. For most storm patterns, we can predict them about a few days in advance. When it comes to earthquakes, the prediction of the magnitude, location, and duration, that's still not possible until the actual event takes place. So when we're talking about earthquake early warning systems, it's typically a system that can predict or that can calculate rapidly the parameters of the source as soon as it's detected. In the case of tsunamis, we can see that there's a large variance in both spatial and temporal extent. And that's mainly because of the uncertainty there is as to the origin or the magnitude of the source itself. And that also reflects as to the difficulty that we have into placing sufficient instrumentation in order to encompass all possible sources of tsunamis. By this, I mean seismic, under the water landslides, volcanoes, and such. Depending on the origin and the magnitude of the source, tsunamis are typically classified as either near field. So kind of what I'm showing here is the typical case of a near field tsunami, which is mostly illustrated by subduction zones, which tend to be close to the coast. Here I'm showing a cable observatory. And along its length, there's like different nodes along its length, and each node consists of a suite of instruments in it. On the other end of the spectrum, we have we have tsunamis that are originated far away from the coast, which are like very long distances or transoceanic. And in this instance, we use a dispersed array of buoys. These are the dart buoys. And these typically consist of a pressure gauge to monitor the variations in pressure on the water column. And then this is stuck. The mouse. Ah, cool. So regardless of near or far field tsunamis, well, you can actually say this for most early warning systems. They all have a similar sequence of steps that they all take. First, they detect an event. They estimate the source parameters. They evaluate the likelihood of this being tsunamigenic or not. They evaluate the impact or the physical impact that it might have on the coast. And eventually a decision is made whether or not to launch an alarm. Most early warning systems have stringent parameters by which they need to abide. One of them is a system lifespan. You typically want a long lifespan. Most underwater cables have about a 25-year lifespan. The latency refers to the time, the delay that is acceptable for the system to take the data, process it, filter it, package it, and possibly transmit it to an on-land data center. It should also be mentioned that what I'm showing here is the cable array, which will actually the spatial coverage and the spatial distribution or the spatial density of the instrumentation is one of the factors that determine the cost, the overall cost of the system. Of course, the more you have, the more expensive it is. So in this case, for a cable array, this is actually planned to be deployed on the subduction zone in the northwest of the United States. It goes from Northern California all the way up to Canada. So you can imagine having a cable array with such length and having multiple nodes along the way will have a very high will require a very high budget. This cable array actually doesn't exist. It's been in the planning phase for more than a decade now, and the reason it's because it has a price tag of hundreds of millions of dollars. And actually, the same can be said to some extent in general, for ocean bottom instrumentation, meaning it tends to be very expensive. It tends to require maritime expeditions. And on top of that, if you take into account the infrastructure and the logistics required to put instrumentation in far away, remote, isolated places in the world, that only compounds the price of the instrumentation. The other thing is that inherently putting instrumentation on the seafloor tends to be a very risky endeavor. It's conducting observations in the ocean floor for long periods of time. It's a very hostile environment. It's definitely not uncommon to have instrumentation either fail or missing out at sea, which I actually had experience in a bunch of times. So it is for all these reasons, all these challenges and difficulties that I've been describing, that the need for a new approach to conducting observations on the seafloor, it's sorely needed. Most often, tsunami observations are either carried out by fixed moorings or buoys, tide gauges. Here, what I'm showing is the global network, the DART buoys that I showed earlier. Worldwide, there's about close to 80 stations deployed worldwide. But as you can tell, the sensor density is very sparse. Hence, the system is only able to provide warning for far-field tsunamis. Furthermore, you can also tell that the world is not equally covered. There's some reaches in the world that are notoriously missing instruments. In our case, like hitting a little close to home, the Mediterranean, notoriously lacking any monitoring from this sort. Typically, it's best to deploy such instrumentation near areas that are prone to give rise to tsunamis, such as subduction zones, plate margins, and the such. And it is for this reason that the possibility of taking advantage of the currently existing infrastructure for telecommunications by introducing distributed acoustic sensing has arisen a lot of interest in the scientific community. It would also, since the cables are already deployed and present in the world's ocean bottom, it would represent also a cost-effective way to gain access to very remote and isolated places in the world. So distributed sensing on optical fiber relies on actually sending a pulse of light down the fiber and only monitoring a small fraction of the light that gets reflected back to the source. The nature of this reflection can either be Raman, Brillouin, or Rayleigh scattering, and depends on the nature of the phenomena being exploited. This back reflection will be sensitive to strain and or temperature. To determine the magnitude of this physical phenomena and where along the cable this is being sensed, we make use of coherent detection of the light being scattered, either in the temporal or the frequency domain. In our case, we're making use of the temporal domain, and we're making use of Rayleigh backscattering. In the case of Rayleigh backscattering, this actually arises from heterogeneities that are included in the fiber. This is a byproduct of the manufacturing of the fiber itself. And these heterogeneities, illustrated here by the different colors, can actually be thought of scattering centers, and they give rise to a change in the index of refraction of the fiber, which give rise to the backscatter. The type of dash that we're using has a particular characteristic where the pulse that it's being generated actually has a chirp. The chirp just means that the central frequency on each location on the pulse itself has a slightly different frequency, and it acts as a frequency sweep. So we don't really need to do coherent detection, but since the chirp itself is actually a frequency scan, this actually maps the frequency shift into a temporal shift. So when we compare a trace taken without any perturbation, so no strain involved, and we have a perturbation with some strain, you actually have a delay, and this is actually what we're measuring in the instrument that we are making use of. Now, when we're talking about tsunamis, we're mainly concerned with the spectrum contained in this yellow region. For the most part, it's in the millihertz regime. What I'm showing here as well are two instruments here. One is the typical DAS instrument available in the market, and the green one shows an improved version of the instrument available in the market. On the typical DAS, we see the 1/f pattern. So that just means that the noise increases with decreasing frequency. This is actually very common in most instrumentation. In this instrumenting case, when we measure a perturbation, this is actually compared to a reference measurement. And the reference measurement might be invalid in the case of, for example, a strong perturbation is being acted upon, or it's also the case for accumulated instrumental drift. And in this case, you need to acquire a new reference. However, when you acquire a new reference, this also has the byproduct of integrating all the random noise in the reference measurement taken. And then you get this effect of 1/f. A new approach was taken with the problem of taking reference measurements by actually taking a database consisting of multiple references taken. And each reference corresponds to a pulse with a slightly different frequency. And this slightly different frequency comprises the database. So in moving forward, when you take measurements out on the field, you actually compare the measurement to all the components in the database, and you take the one that's most closely resembles the measurement taken. And then the next step would be to find a finer calculation of this of the delay that I showed earlier. What I'm showing here is actually the same instrument, but this was taken with a more stable laser. But what really makes the difference in this case is that the acquisition was made at a higher repetition rate, at a higher sampling rate. So this was actually taken at 1 kilohertz, and this was taken at 1 hertz, I believe. The noise floor actually improved by 2 orders of magnitude. However, due to limitations in the lab, since this was a very high acquisition rate, we didn't have enough memory in the oscilloscope and the equipment we have in the lab, so we couldn't acquire a long enough period to go into the sub-millihertz regime. But we have good reason to believe that this would extrapolate further down to further below in the frequency regime, if we had the capacity to do so. Now, as I mentioned earlier, the instrument primarily measures strain. So here I'm just showing a little definition of strain. So I'm drawing a parallel comparison. For example, we had 2 geophone instruments separated by a distance. The strain would be just the displacement of these instruments divided by their length. In a DAS instrument, this L is actually referred to the gauge length, and this is to some extent adjustable in the instrument. Just as a little side note, when we're using cables, we're not using cables that you might be familiar with here on land. Cables on the seafloor tend to be a lot more robust because of the hostile environment that I just mentioned. They need to be protected against water ingression, pressure, temperature, salinity. So they have multiple variations on the protection and armoring of the cable. Typically in the shallow regions, you use a heavier armoring, where the deeper you go, you can afford to go to more slender, more narrow, smaller cables, I would say. Now, one potential challenge we might face is that typically tsunamis, the way to measure tsunamis is by the by the pressure differential caused by the traveling tsunami wave. However, when we're using DAS instrumentation tends to be more sensitive on the axial direction along the longitudinal, so along the cable. And the sensitivity tends to decay as a cosine squared function. So needless to say, a normal strain, which is the case for pressure, that would correspond to what's called the blind spot for the instrument. But in spite of this difficulty, DAS instrumentation on the seafloor has already proven to be capable of recording pressure variations. In this instance, pressure variations were recorded from surface gravity waves or ocean waves. So here, this animation just shows like a 1-minute glimpse of 8 kilometers of cable being deployed. And here we see that the evolution of the amplitude for the time that was this running a while ago. So we see that the amplitudes tend to increase when we're reaching the shore, and they tend to decay as the depth increases. And this is predicted by the linear theory of gravity waves in water. Recently, about a month ago, the first reported detection of a tsunami using seafloor DAS has been reported. In this instance, the team used about I believe it was like about 60 kilometers of cable from the Pacific Northwest of the US, where they managed to detect a far-field tsunami that had about a 5-centimeter water displacement at the source. Signal being detected here. Although the signal itself had a low signal to noise ratio, meaning that the signal was comparable to the background noise of the instrument. But in spite of this, this offers a good indication of the possibilities of DAS to actually record tsunamis. Furthermore, this study was mainly a field observation, so it didn't really offer much in the way of an analytical explanation as to the mechanics as to how this detection came about. So with that in mind, and in order to better estimate how the sensitivity required of DAS to accurately detect tsunami waves, we derived a model where we estimate, or we estimate the source, the strain that we would detect on the seafloor, mainly only due to the tsunami wave itself. So there's two phenomena that we're considering here. One is due to the pressure variation induced by the wave itself. And this is divided by two phenomena. One is the Poisson effect on the cable itself. So you put some pressure on the cable, and it causes some elongation along the longitudinal. The other effect from pressure we're considering is that of seafloor compliance. So it's just the squishing of the seafloor and the horizontal compliance that corresponds to the pressure. The other phenomena we're considering is the shear strain that it's impinged on the seafloor due to the motion, to the flow of the tsunami, represented down here. So in our model, what we derived here, so what I'm showing is two instances. So one is for the case where we have about a 10-centimeter water displacement. The other one is for the other extreme, about a 1-meter water displacement. The top row corresponds to the effect due to pressure. This is due to the shear effect, and this is the total compressed effect. We noticed that on the total effect, so the total just includes both of them. But we see that by and far the dominant effect is that due to pressure on both instances. The shear effect only takes a more it doesn't take a dominant role, but it becomes to take a little more effect when the wave itself is closer to shore. and also, of course, with the larger water displacements. In this instance here, I'm showing a propagating tsunami wave. This is the case for 10 centimeters. This is for 1 meter as well. This should have mentioned this earlier, but the different colors correspond to the different depths at which the tsunami originates. The green line represents the noise floor of the instrument that we're using for this study. In all the graphs I've shown so far, we are well above the noise floor of the instrument itself in all instances. So we seem to be in a good starting position for detecting tsunamis. A little worried that we had during this study was the potential impact of temperature, because the instrument also detects temperature. Temperature signatures can be close or can overlap to the tsunami frequencies in the millihertz. However, there's many papers that have shown that it is possible to detect temperature on DAS instrumentation. However, if we notice most of the detections done, the temperature has orders of magnitude lower velocities. Right here. Has lower by several orders of magnitude difference to that of tsunami propagation. So we're fairly confident that we can filter these signals out. The other source of temperature signature might be that due directly to the tsunami itself. However, temperature signatures due to the tsunami have not been very well recorded. Most of the records we have of temperature variations due to the tsunami itself have been recorded not accidentally, but fortuitously, you could say. Because a lot of the dart buoys, they contain pressure gauges, and the pressure gauges actually contain an internal temperature sensor, which is the primary objective of this temperature sensor is mainly to calibrate the drift of the instrument. It wasn't really meant to be used as a temperature sensor in the environment itself. However, there's been a few studies that use this internal temperature as a proxy for the temperature variations in the environment. But since this temperature sensor doesn't really have the accuracy for most temperature studies, there's no clear available data for temperature due to the tsunami. So lacking such temperature data, we did a first order approximation of what temperature we might expect from a tsunami. So if we consider the water particle motion for a tsunami, it typically has an elliptical shape, where the horizontal displacement tends to be about 10 times larger than the vertical displacement. The horizontal displacement tends to remain constant throughout the depth, while the vertical displacement tends to decay. So if we consider, let's say, a water displacement of 10 centimeters for a tsunami, and we the 5% slope between the continental shelf and a subduction zone. And if we extrapolate this horizontal displacement along this 5% slope, we would get a displacement of about vertical displacement of about 5 centimeters. And if we consider let's say like a general temperature gradient for the open ocean, the vertical temperature gradient of 2 millikelvin per meter, and with this displacement on the slope, we would get about 0.1 millikelvin. The correspondence between temperature and strain on the instrument is given by this relation. So we would arrive at a nano strain signal from this scenario here. Now, 1 nanostrains is definitely above the noise floor of the instrument. However, this is still orders of magnitude below what we estimated earlier for the signal due to the tsunami. So it's not a significant hindrance for the detection. So in order to further illustrate or to validate, to prove the potential contribution for DAS in tsunami early warning systems, we made use of a synthetic data set that consists of full physics simulation. So full physics means that it includes seismic, acoustic, and gravity wave fields. The simulation was in 3D, and it simulates an earthquake rupture and the tsunami that it induced. So the simulated scenario, what we have here is a simulated megathrust earthquake taking place on a planar fault here with these parameters. So it has about a 200-kilometer wide, has about a 16 degree slope, dip, going down to 35 kilometers. It has a uniform water layer of 2-kilometer water depth. And in the simulation, we simulated multiple arrays of receivers, which simulate multiple cables being deployed in the vicinity and over the fault itself. So we simulated receivers on the sea surface and coupled to the seafloor. The receivers on the seafloor, from these, all receivers had a velocity data on it. So we integrated the velocity to get displacement and taken the average of displacement between two receivers. We would get about an average for the water displacement on the vertical. For the seafloor, we did exactly the same. So we integrated velocity to get displacement, and we calculated strain between the two receivers. We know the separation between them. Each pair of receivers here is meant to mimic or simulate the gauge of the DAS instrument. And then the next set of receivers is about 450 meters placed apart, and the pattern just repeats itself from there on. So it's an example here. I used the receivers on the top of the water column for these. I'm illustrating here the case for the array at y equals 0 and the array at z equals 0. So we get these results here. So this corresponds to the broad spectrum of the water displacement. And once we filter out for the tsunami frequencies and wavelengths expected, we would actually arrive at the tsunami signal itself. Now, when we look at the data from the receivers that are coupled on the seafloor, we get a broadband signal that's mostly dominated by seismic and acoustic wave fields. So at the onset of the simulation, we are dominated by seismic phases having a kilometer having about 3 kilometer per second velocities. So once the rupture propagates on the fault, once the propagation ceases, the field is mostly dominated by static displacement, with static deformation. The second row here shows this same data, but processed and filtered in order to be able to discern the tsunami signal here. The bottom here shows the expected tsunami signal, but this is calculated from the water column, from the top of the water column. It should be mentioned that this simulation didn't simulate a cable itself. So the tsunami signal we're getting here is only due to the compliance of the seafloor. So this explains the reason why this signal here is about 2 times stronger than this one here. The other challenge we were facing is the relative magnitude of the tsunami signal compared to the broad spectrum. The broad spectrum is several orders of magnitude larger than that of the tsunami. And this represents actually one challenge that we will face if we try to detect tsunamis near the source, where the tsunami signal is going to be obfuscated or buried deep below the stronger seismic and acoustic fields. So in this slide, I'm showing just a summary of the results. So this is the expected strain signal that we would expect for each one of the arrays color-coded as such. We notice that the strongest signal we get is corresponds to the array parallel and traversing directly over the trench itself, which is to be expected since the tsunami energy tends to mirror the displacement of the fault itself. So just general closing remarks is that based on the analysis of our derived model and the observations on our simulated data set, there's a very feasible prospect to detect tsunamis with DAS. And this would actually represent an unprecedented opportunity to monitor and anticipate tsunamis. And this would be attained by allowing us to monitor in a manner that's continuous, real time for tsunamis and with sufficient density and location for sensing opportunities. Well, one big thing to make this possible is that the improved low frequency DAS unit to become a reality, to be available in the market, because currently it's still in the research and development phases. And that's pretty much what I have. 10 minutes.